Değerli arkadaşlar, tekrar hoş geldiniz. Artık bir gelenek haline gelmiştir. Bizim yaz okullarımızın bir parçası olarak aynı zamanda public lecture serisi düzenliyoruz. Her okulda mutlaka bir hocanın bir public konuşması var. Onun dışında ayrıca bizim seminer serilerimizin biri de public lecture serilerdir. Çeşitli yönlerden böyle. Çünkü biz kamu kurumuyuz. Devletin parasıyla ayakta varız, milletimizin vergisiyle. Dünyadaki her bir önemli kendine saygılık gösteren kurum kimi, bunun outreach programı olması lazım. Halka açık olması lazım. Yaptıklarını anlatması lazım. Geniş kitlere için. İşte bu public lecture'lerin de aslında amacı budur. Tamam, kısacası. Şimdi hocamız da anlatsın, İngilizce konuşun. TÜBİTAK Research Institute for Fundamental Sciences organizes Scientific Türkiye Public Lecture Series with the participation of distinguished scientists and great speakers of the world. As traditional, as a part of our summer schools and independently. The aim of these events is to share the passion for science and research with a wide audience, as well as to foster scientific curiosity and scientific culture in the society. I like to cite repeatedly Einstein, who said, "Curiosity has its own reason for existence." Professor Sergienko from Boston University has kindly agreed to give a great public lecture under the title, "Could Quantum Mechanics Make Technology and Our Life Better?" Please have a pleasure of listening our great speaker.
All right, good afternoon. So I guess it's basically the same people, just public lecture now. Well, I didn't know what would be the audience, and since it's a more general discussion, the presentation will be in more general terms with less specialized information, although since I didn't know what would be the audience, so I introduced a little bit of what you already have seen in terms of the qubits, because that's the base of quantum computing that we will be talking today about, because it's one of the biggest, most widely discussed subject these days. So basically, could quantum mechanics make our technology and our life better? So better technology and better life. Let's see what it is and what kind of promises and results it has. Again, the importance of this area of quantum physics basically has been recognized by awarding the Nobel Prize to three great scientists who contributed a lot to the quantum information in optics. All three of them, they did experiments in quantum physics using optical systems. You know that previously several Nobel Prizes were awarded to physicists who did quantum physics with cold atoms, for example. The first question is why? Why there is so much attention to quantum physics these days? While the quantum theory has been established basically a century ago, almost, and lots of founders of quantum mechanics, they obtained their Nobel Prizes at that time. And then there was basically kind of long time of basically break in the attention. There were many other subjects developed And at the end of last century, around like 80s, 90s, basically people start talking about something that later on got a name, second quantum revolution. Why second? Because the first one was the development of quantum theory by itself. And second is what you can do with quantum theory in practice. What you can do else, in addition to just educating scientists and students. Is it possible to do something in addition? Well, the first subject that was coming into play and gave substantial interest to the whole field was quantum computing. Well, basically, what's different between quantum computers and classical computers? As we discussed, the classical calculates everything with transistors that execute logical Boolean gates, 0 and 1, and manipulation between them. Well, qubits in quantum domain, they exist simultaneously and in superposition. You don't know which one is which until they act or until you measure them. Well, the medium, the majority of classical communication devices are based on transistors to create logical switches. Basically, a transistor is a device that changes the voltage or current. For quantum systems, you have to find something that has those qubits. It could be trapped ions, superconducting loops, let's say, quantum dots, diamond vacancies that can create qubits. Basically, we'll talk more about this later on. So, how many? The amount of transistors per square area, like per square millimeter or whatever, is really dramatic these days. You know, the smaller the size of the transistor, the more of them you can pack. As a matter of fact, that was also, from one side, it was the base of the famous Moore's law. Right? From the other side, it led to the situation that the speed up of modern computing and of number of elements you can put there got slowed down lately. And the reason for that was extremely simple. It's basically a heat. Many of, well, I don't know, if still some of you remember, well, it's hard to say 80s or 90s or early 2000s, there are new computers were appearing almost every half year, every 6 months, every year, and the speed of computer was growing, like 500 megahertz, 709 gigahertz, 1.5, 2 gigahertz. For the last almost 10 years, it's unchanged. Well, we know why.
You can't make the transistors daha küçük.
Yeah.
Thermodynamic. We can't cool
What do you
enough.
mean by that?
We can't cool processors enough for its viable use.
So the speed means, well, with gigahertz, kilohertz of switching from 0 to 1, right? You have two logical levels, 0 and 1, and you have to switch. The speed of switch in the transistor depends on what?
Transmission lines between two levels,
No, it's not transmission lines, it's just the transistor itself.
like gate
Gate, yeah.
capacitance.
Yeah, so what defines the speed?
Like gate capacitance times the gate resistance.
Capacitance and?
The resistance of the wire that goes to
And?
the gate. So when you multiply them,
Huh? Yeah, electrons, the flow of electrons that is called
current.
The fact,
If you find the
if you take two levels, 1 volt, or let's say 0 and 5 volts, TTL levels, and you want to switch in 1 nanosecond or in 1 picosecond, the difference in the speed, right? How much higher current you have to run through this system. The higher currents means, yeah, that's it. As simple as that, basically. And there was another reason, basically, when speed went really high, when you have this current, accelerating electrons, what they're doing?
Collide with each other.
electromagnetic waves are
They start to irradiate.
radiation.
You know, your circuits are glowing. In addition to warming up, they really glow radiation from accelerated electrons, so the radiation. So basically, it's thermodynamics, yes. The thermodynamics stops that. And that was one of the reasons people start to look for something else. Can you do something else? It's still not the end of the road. It's still basically what they try to do after that. They say, okay, if we have one layer that is really heating, okay, let's keep the speed constant. Let's make several layers, right? That's what it is right now. Basically, how many sub-processors you can put on the top of each other. And at that time, the issue came up, can quantum somehow speed up things? And that's where really we come into the issue, how the quantum can speed up the computation. And the answer to that is really, as I said, it's not one-to-one, because it's like apples and oranges. The speed up of calculation means conventional computer will be calculating those differential equations that describe the properties of the quantum system in comparison to the alternative. An alternative is can be a quantum system that executes the same Hamiltonian that the system you're trying to investigate, and you self-assemble it, and you run it, and you get the answer quicker than the computer finishes. Conventional computer, limited by all these parameters, all the limitations, arrive to the answer. So that's the competition. And then the question is, how many of these qubits do you need? And that's a good question. We'll talk more about this later. So power, computational power, linear. In classical, there's the quadratic or exponential, depending on the system, with qubits. Basically, then the first one, actually, like speaking of motivation for this, the first motivation I told you that Shor's factoring algorithm was the first one to motivate this, and in order to do the factoring of prime numbers, in principle, the process mathematically is well defined. You can do it, the same as solving system of 1,000 differential equations. You can do it. The question is, how long will it take? The same is here. So if computational power is exponentially greater, then you can reach the power that you can solve the problems that linear will take too long. Okay, errors. Basically, this is the kind of laundry list of major parameters that affect the technology development and usefulness of what is developed. So, errors. In conventional computers, it's pretty low. Well, it's getting a little bit harder because remember, the 0 and 1, as I told you, so transition between 0 and 1, the sharpness of this transition defines how much current you need. So in addition to making like capacitors smaller, what people have tried to do to reduce the heat, they reduce the distance between those levels. Remember, original computers were running on like 5 volts, then there were 3.3 volts, then 1.7, 1.3 volts. So they tried to minimize the step size to reduce the heat. But still, well, even when you go to such a small distance, there is a problem of noise, but it's still well distinguished. In quantum systems, the noise is much more important and affects systems stronger. Well, here is another very nice and important comment the regular computer used for general purpose computing. Basically, whatever you want, you can put any program there. The quantum computer is used for optimization, factoring, or any other purpose, but it's specifically designed for the use of that, basically. It's very hard to reconfigure this device and still be efficient.
Don't we use room temperature?
Room temperature for what?
For design.
Well, we'll come to that. Basically, the question is, it's all relative. We'll talk about it. What it's based on? Actually, it's based on what we discussed in the previous 2 lectures. So, you see, quantum mechanical, which explains the behavior properties of atomic, subatomic particles such as electrons, neutrons, and photons. Basically, it's something that you have never seen in your life, and now you have to learn how it operates. Basically, I told you that's the biggest step in the comprehension or understanding of the thing that people are struggling with. That's why lots of people consider quantum mechanics as a heavy theory, because it's hard to kind of touch it, because all our world, all what we can touch is completely classical. There is no feeling what it's supposed to be. Okay, superposition. Well, we discussed superposition. So in many possible states at the same time. And in which particular state it will come out depends on multiple situations, multiple parameters, and also on probability. It's random. Entanglement. Well, exactly as we discussed. Well, like Einstein calls spooky action at a distance. Well, now I hope you understand that there is no spooky, no action at a distance. Sorry, no action at a distance, and it's not spooky. It's basically what you create, so much you have. You created the system with particular degree of correlation and superposition, and you can send these 2 particles anywhere you want. You always will have predictable result of the measurement device applied to this system. Always. There is nothing else. So you make a good entanglement, you will have high violation of Bell's rule. You make a bad entanglement, you have bad violation. All right. Observation. Well, again, superposition and entanglement only exist as long as quantum particles are not observed or measured. Exactly, I told you. So as long as your system is isolated, it behaves as a quantum. Everything inside is unitary, behaves as in accordance with Schrödinger equation. Everything is nice, quantum mechanics is applied. The minute you start to come with your classical measurement device and project your system on the classical device, you just realize one of the possibilities, one of the probable outcomes of superposition. So with probability that will be square of the amplitude of every option. And then the last one is the qubit. So quantum bit. So it's an element with 2 states, but they are equal, indistinguishable, but you don't know in which of the states the system is positioned at this particular moment. Again, just what you have seen already. What is the qubit? It could be either spin, up, down, or photon polarization. Since we start talking about different platforms for quantum computing, there is one more, superconducting qubits. Who knows what the superconducting qubit is about? Yeah.
I know just.
Like, how do you get the qubit in superconducting? Yes?
There are 2 types, I believe. One is considering the flux going to a Josephson junction.
It's a flux relator, right? So basically, this is the kind of, what is the spin? Spin is some parameter associated with precession of electron, right? This rotation of electron. So, well, it's a natural created in atoms and anywhere electrons exist, right? So how about, can we create artificial speed? If you create a small circle of superconducting material, then there will be supercurrent in there, right, in superconducting condition. So what is a supercurrent? It's a motion, a circular motion of electrons, right? So you can associate a spin with it. Well, if it goes this way, it will be one spin. If it goes the other way, it will be this spin. If you connect them like this, then your system is still at the nanoscale. For any observer, it will be not, you cannot distinguish either this or that. It's simultaneously involved. So that's really artificial speed. That's what the superconducting unit for the quantum computing is about. And photon polarizations. Well, speaking about photons and quantum computing, there is the big, I just want to point out, what's the biggest difference between real particles and quasi-particles like photons? We discussed the photons, and what is a major consequence of the situation that we already discussed? Orthonormal base of electromagnetic field and no energy transformation between modes. It means no interaction between photons. No interaction actually is not good for computing. Because, well, for physics is not good. So if you want to simulate system, quantum system, where you have interaction of parameters, and you have particles that are not interacting, it's very hard to do. So, but also, because it's no interaction, it's very difficult to execute a major element of quantum computer, which is the control node gate, and we'll come back to that. Okay, again, qubits are good for the breaking codes. By the way, again, the original idea was to have this exponential speed up of quantum computer in executing particular tasks. In this particular case, it's a task of factoring prime numbers to break the RSA code. Originally, again, it's been a long time ago, every year RSA have been doing competition. I still remember times when the RSA encoding was like 56 bits. Today it's 256, right? So then the double why? Because every year they send out the code and ask, can someone break it? And people try to use regular computer power. Young people, they were calculating for example, they broke one of the codes like in 9 hours by chopping the mathematical program in pieces. So this problem, each piece going to young researchers at good institutions with nice supercomputers. They use them basically legally overnight to calculate their own pieces, send it back, and then reassemble and do the final thing. And some use it like the people at Los Alamos, at CERN, everyone who has a supercomputer, they participated, and they broke it. So they had to increase the level of encoding. So basically these days public codes, they are pretty lengthy and heavy overhead to have it. And in principle you still can do it, you just need enough computer power and time. For some of the secrets, state secrets, for example, the problem is you can record it today and wait 5 years until computer power will be greater. You can decode it there. And some governments, they don't want things be decoded for 50 years or maybe even 100 years. They're afraid of these things. So that was a real threat at that time, and it really drove the development of quantum computing. And then again, this is the search algorithm, which I started to say it's about 1.5 algorithms. And by the way, this is the big problem, because this part, as I told you already, So simulation of quantum processes such as chemical reaction, molecular dynamics, and so it's quantum simulation. It's a nice, interesting thing. And in a minute I'll show you that it's really exciting. It's old idea and really kind of physically interesting. But it's not the one that was driving the quantum computers originally. And the other issue is, so 1.5 algorithms that really benefit from quantum structure. And it's still, the situation is the same. The whole field is suffering from the lack of new quantum algorithms. I still remember, I don't know how many of you know.
So may I ask a
Yeah.
question? I'm wondering this, like, it is quantum computing. It is the operational one because we instruct the system with the algorithm, or is the genuinely, entanglement merged because
Yeah,
of the atomic size?
it is based on the system that executes quantum control node
So
using
the
qubits.
atomic size,
The unit, the
Unit.
gate,
yeah.
is classical is based on transistor gates. This one is based on specially designed quantum control node gates. And you particular sequence of these gates and particular operation gives you outcome that will come significantly faster than if you try to execute the same using convention.
Entanglement process.
Entanglement is the base for the control node gate.
So it has come from the algorithm that we wrote.
It's no, how to say,
I mean,
the design of the gate can be any, but the function, quantum function, has to be control node. And control node comes from the entanglement of the
so
participating.
it's kind of an operational entanglement, I mean. Or genuinely because of the knots, it is merged, quantum factors merged.
Well, you cannot use a classical system to execute quantum control node, basically, because you cannot do quantum engineering. That's why. But I think it maybe will become more clear when we go through examples of the things. So many years ago, the discussion was going, and there was a big need for new algorithms. Basically, in '99, we had a nice conference in Hungary, and David DiVincenzo, I don't know, maybe some of you have heard this name. In the past, he was a big kind of guy in quantum computing. He started the DiVincenzo criteria for the system of quantum computing. He said that we desperately need it, otherwise the field will die because no new algorithms that genuinely benefit from quantum. Actually, speaking of which, it's a good question what you asked, because this all can be done classically. This process, basically, the fast factory, can be done, actually, it's the same, yeah, it can be done classical, but very slow, it's still the same thing, sorry. Okay, so basically now there's a division of this, and so simulation of systems, and this one is going slower, this one is picking up speed right now, lots of examples, so people start talking about the drug discovery, molecular compositions, and everything that can be done using quantum computers. Well, again, the qubit that we discussed, it's a combination of 0 and 1. Again, Pauli matrices that's supposed to move the 0 and 1 around for the purpose you want. This is the key. The key is the control node gate on 2 qubits. And these 2 qubits must be in the entangled state to execute. So what does it mean? It means you have qubit 1, you have qubit 2. This is control, this is called control, this is target. How this gate acts. So if your control here, control is 0, then the second one was 0 and stays 0. If the control is 0 and second one is 1, it still stays as 1. When control is 1, then the second one from 0 flips to 1, and from 1 to 0. That's a table how this system is supposed to operate. And this is basically 2 layers, two rail system, and the states of this, and they are, as you can see, it's a quantum states. It's a bra states here depicted like as a quantum vectors. So you have to change the quantum vector based on the state of this quantum vector, which immediately brings the interesting issue. So to change this, knowing what state of that, how to do this? Because this is qubit, it could be either 0 or 1 equal. So your system, full systems, has to be sensitive to relative relationship between this and that. So to some extent, you have to be able to know what this state is, and based on that, act on this. That's why it's called control and target. So there should be some degree of interaction between these two, and that's why I'm saying photons are not good for this, because there is no interaction with the photons. Yes?
Like, for example, I still, like, I couldn't fully understand how CNAP works, because, like, how you can preserve the state of the control qubit, because you need to measure it so that you can change the target.
Oh, you have to create the system where the one affects the other one without measurement. That's the whole trick. How to make this system such that it acts like this, but without any external classical measurement. In fact, you cannot afford to have extra measurement, because then it will break your system. You see? And if you need to have multiple of that, because the whole idea of Shor's factoring algorithm is quantum gate, control node, sequence of control node gates, and read it out only at the end. And it's all supposed to be in the quantum state, self-coherent. So that's why you may have heard about the competition, who can keep those gates longer. Because you have to have first gate, second gate, third gate, 10 gate, and the outcome of the 10th gate still has to be in phase, coherent with the initial one. That's the biggest problem of quantum computing. All right, so that's what it is, and what is quantum entanglement, since it was originally a public lecture, so we've seen already a little bit more about that. That's something that resource that can fuse quantum computer or quantum communication network. Basically, this is Alice, this is Bob. If we create here the entanglement, then we can distribute it. I told you, so it can go far away, and whatever is here and there is still the same property, has the same property as here. So if it's entangled here, it will be entangled there as well. Well, this is correlation versus entanglement. Again, I didn't know that the audience will be different or not, so this is again a reminder that entanglement, it's non-factorizability of the state of two particles or two subsystems. And this non-factorizability can come in the classical domain in the form of classical correlation, and it will be non-factorizability of probabilities. And it's a common coherent theory. Or if you go in the quantum domain, in the domain of wave functions, then we deal with something that is originally Schrödinger likes to do, use the non-factorizability of two wave functions. That's really what the quantum entanglement is about, and we already touched upon several issues and several kind of potential problems, how to create it and how to preserve this entanglement through the operation. Well, again, what it's good for, entanglement, you can test foundations of quantum mechanics. Yeah, we discussed that, so Bell's inequality violations and everything. Sometimes it's good to resolve paradoxes, to learn that how quantum mechanics operates. Quantum teleportation, we're not going to talk about this, but it's another special effect what you can do with qubits. Quantum key distribution and quantum cryptography, I'll touch on that because it's a popular topic. I think it deserves to have some general attention first, and then there will be a lecture tomorrow on more details of that, for more specialized technology. Quantum computing, we discussed this a little bit, and then the quantum sensing. Again, I'll touch a little bit about that. I will have a whole lecture on quantum sensors later on. Not all of them, but some examples of quantum sensors. So, quantum computing. As I said, so there are several subsections of quantum computing. Quantum emulators, simulators, quantum annealers, noisy intermediate scale quantum computing, and universal quantum computers. So what stays behind those names? So, I don't know, maybe we can come from this side. So universal quantum computer, its ultimate goal, it's something that can have sequence of control mode gates, a very long sequence, and you can program it to do particular functions, and that way you can execute quantum algorithms. That's an ultimate goal. That's what will do the Shor's algorithm. Okay? We'll talk more later about time scale. Noisy intermediate scale quantum computing. Intermediate scale. Basically, the question is, intermediate scale means limited number of qubits and limited number of gates. And not very high gain, not very high quality qubits. Noisy. Because again, noise, what the noise is? Noise is something that violates the isolation of your system. If your system is isolated, its ideal quantum system behaves ideally. When you start interact with environment around, the energy starts to penetrate your system from outside, and this is something you don't want it to be there. It's your noise, basically. And that's what causes decoherence. Decoherence is another way of saying you have quantum system, then noise starts to come in, and it starts to lose its quantum properties. That's what decoherence is about. Quantum annealers, it's kind of a very interesting system. You create a bunch of qubits, but you didn't put them in gates. You just connect them. And then you try to measure the distribution of energy between them. And you do this at a very, very low temperature. So the noise, because usually, originally, it's done with superconducting qubits. So superconducting by itself, it's a process that exists at very low temperatures, right? The other thing is the manipulation of all these bits, it goes at the speed, basically the round trip, for example, all the motion of electrons is associated with motion of electromagnetic field. And the speeds of that in gigahertz. Gigahertz is usually RF, radio frequencies. And in order to do basically read out of the system, you have to distinguish one photonic quantum from the other quantum. And now we come into another big problem of photons. And the problem of photons is its energy is h omega, right? So you have to have this coming, and then you would like to detect. The question is, in order to detect something, the energy of this something has to be greater than the noise around or noise inside the detector. And the question is, what is the major source of noise in physics? Say again? Not even vacuum. No, well, vacuum fluctuation is there, but it's pretty low. Above that. Thermal fluctuations. What is the measure of thermal fluctuations?
Should be infrared.
Well, it's infrared, right? Why it's infrared? What is the measure? How do you know it's infrared, not visible? Or how much it is in the infrared, how much is invisible? KT, exactly, the Boltzmann. the introduction to thermodynamics, KT, right? So that's the level or average level of fluctuations of thermal system. Okay, so if you have energy of the photon is H omega, energy of the noise is KT. If your H omega substantially greater than KT, you can easily detect. The problem starts when your H omega becomes comparable to the KT. Now you cannot distinguish the noise photon, your detector cannot distinguish noise photon from the real photon, right? Not talking about the fact when this one becomes smaller. However, there is a trick exists how to fix the situation. You take KT and bring the T down, right? Now, it was not visible there, but then when T goes down, down, down, it becomes visible, right? So that's why all the operation of superconducting qubits goes not only at the temperature at which this particular material, metal, is superconducting, because many metals superconducting at Kelvin, like few Kelvins, basically. But the operation of quantum computing computer goes at like 10, 20, 30 millikelvin. That's how much you have to put it down there. Okay, so, but this one is basically it's interesting. So you put the circuit, and what you do, you measure the standard things. So, but then what you do, you kick it out a little bit out of equilibrium and allow it slowly evolve back to the situation where energy will be kind of normally distributed between all those qubits. It's called annealing. Because regular annealing is the same process. You warm up and let it slowly cool down, and then it settles more uniformly. Here, it will settle proportionally to connections between those two qubits, between many qubits. Like 1,000 qubits, you basically look at in a particular way. Which way? This way is supposed to reflect particular problem you're trying to solve. And then the energy will go down, and it will tell you the optimal distribution of energy across those qubits. That's why some people say it's not really quantum, because you will kick it out of the quantum domain and then allow it go back to the quantum domain. It's more like annealing. That's how the D-wave computer works. What it's good for? It's good for optimization. So basically you have 1,000 parameters and you want to satisfy particular conditions. Usually you have to check all possible combinations. Here you just set up wires and run it, and you measure final distribution of energy, and it tells you what it will be, what the answer to this situation. So that's what the quantum annealing is about. And the rest is emulators, or simulators. It's basically you have a quantum system the same way. You design combination of qubits, manipulation, whatever, to resemble some quantum system you try to study. For example, you have two atoms forming the molecule, and you know all the connections between them and so on, and you just do this with your qubits. You say this qubit interacts with this one with this strength, which is strength of particular connection and so on, and you just run it and see what the outcome, and compare with the calculation. That's basically what it is. And at the end of the day, so this is really distant future. This is what we have today, but not too many of them. This one too. Basically, then the question is, there is competition of computational complexity of solving equations and running the model of the quantum system. When you will get better result, when it becomes useful. And the answer is, this would become useful if you can have like at least 10,000 to 100,000 qubits. Like 10, 100,000 qubits can simulate quantum system that you will have trouble to simulate using computer. Okay? So that's kind of scale limitation for this task. So speaking of the simulation, as I told you, the word simulation is not extremely appealing to program managers and who give money for research, but originally that's what really was the beginning of the quantum computing. Basically, Richard Feynman, in his lectures, you can read this, that if nature isn't classical, then you want to make a simulation of nature, you better take in quantum mechanical. Basically, you need to, if you want to simulate the nature, you do it in the quantum mechanical way. Basically, you need to have a quantum mechanical simulator of it. And that's really, it's 1982. It's given that. In fact, it's funny, but one friend of mine, Jim Franson, he was a student at Caltech at that time, and he was told that students were aware that Feynman is working on quantum computing. That was the kind of, his idea of quantum computing was as early as that time. Of course, no one done anything after that, but it came back later on. And again, it came back, got a really big push through the Shor's algorithm, but when people realized how difficult to do the real Shor's algorithm, they went back to the idea of quantum simulation. Still, this area can have lots of useful applications if you do it right. Now, what does it mean to do it right? To do it right, it means to build up a system with thousands and hundreds of thousands of qubits. How we can do that? Well, what physical systems can potentially produce qubits and entanglement between two qubits, at least between two. Okay, so superconducting loops, we just discussed that. So you can have, you print nanoscale capacitors and some circles for the currents, and microwaves, RF frequencies are going through. So that's your superconducting qubit, and to operate it, you have to stay at tens of millecloud. Trapped ions. Trapped ions is a nature-given qubit because it has nucleus and has electrons, and the electrons have spins. So some of the spins, they are in superpositions because of the structure of the orbitals. You can have more electrons, and the selection rules put them in particular states and so on. That's a great majority of effects have been demonstrated originally using cold atoms. Silicon quantum dots, that's the latest comer in this area because you have to make like artificial atom. Artificial atoms in semiconductors. The problem is the same as here, noise in semiconductors. That's really, you have to fight. Because the semiconductor, it's a solid state material with phonons and everything inside, it's your noise. And people, step by step, improving the quality of those qubits. Topological qubits. Well, that's a little bit more mathematical abstraction. I haven't seen too many cases when people were able to do the braiding operation, because this is called braiding, when you change the, move from this point to that point and like this way. Diamond vacancies. Well, it's one of the example of the area that is called quantum dots. Quantum dots, it's something like you have something really very, very small dot. But in behavior, it resembles the atom. It's like artificial atom. And there are many different structures where it is done. And diamond vacancies, it's basically the matrix of diamond, and if the carbon is missing and substituted by the nitrogen, that's where you have changing properties, basically. It's like an atom in the surrounding, or different atom in surrounding of other environment, and it behaves like artificial atom, and you can get some, the energy levels of this system can be resemble the energy levels like of trapped ions, for example. Then neutral atoms. For that you need lattices of them. This is lattices made of optical fields, optical traps. It's like standing waves in optics, and atoms are kind of located in all these elements. And photonics. Photonics qubits. We discussed this a lot, how to make them. Beam splitter sources, beam splitters, and so on. So that's what technology is offering us. So the idea is to go from this is early stage of classical computers, this is early stage of quantum computers. So it looks kind of similar scale, right? And the idea is that maybe like 50 years from now, this will be converted into something that this was converted over 50 years. And we know the result of that. Well, what do we have in terms of quantum computers sizes these days? So this is a D-Wave system based on annealing, but still the debate is ongoing. Is it really quantum or is quasi-quantum or whatever? But you can see the size of that. There's there are huge DUR inside there of helium and dilution refrigerator because it needs to operate at tens of millikelvin. The same is with regular simulators. Regular simulators, there are a few players like IBM, Google, some other companies, they're trying to build up. So I just want to point out first in the closed. So see this guy and see the size of this. This is the dilution refrigerator, a special type of refrigerator that can reach tens of millikelvin at one stage of this, which is on the bottom. This is what, when you take the cover out, so this is about like more than a meter in diameter, and the chip itself is sitting right here. All this is amplifiers, this is wires, so each layer here has different temperature, from the like room temperature on the top and going down, down, down, down to tens of millikelvin over there. And this is all about 128 qubit. 128 qubit. Now, in order to, well, let's just talk about this, why it's problem, why 128 is not so much. Remember, we were discussing that to do something useful, you need about like 10,000 to 100,000 qubits. Well, there's still a future. What is today? Today, the situation is, you remember probably like 6 years ago, 5-6 years ago, Google was so kind of advertising the quantum supremacy. They say, okay, we have new chip with 49 qubits and we'll demonstrate quantum supremacy. We can solve the problem on this chip faster than the regular computer will solve the same problem using conventional calculation of equations. And then there was quiet after that for 2 years. And then they say, oh, we have a new chip, it has 70 qubits and then 100 qubits, and then they found some kind of problems where they show some benefits and advantages. The question is, what happened? Why it was not so easy with 50? The answer is very simple. You could have basically all these qubits, how you do the simulation. You have all these qubits and you try to connect them in a particular way to simulate interactions in the system you're trying to simulate. Okay, each single qubit, they were thinking is really good quality. It's the fidelity of entanglement in that qubit, or fidelity of qubit and the connection between the how entangled you can entangle it. This next one was like 0.985, 98.5%. It's a lot, really, a lot. But then they start to run it and they found out that because of these qubits, they're all kind of separate, we put them in the system, so the fidelity of the whole system is the product of fidelities of those if you take 0.985, multiplied by itself 49 times, or 50 times, I think it's 49 qubits, you will arrive with like 0.49 something. It was less than 50%. So you have a result, fidelity is 50%. In information theory, fidelity of 50% means
Nothing.
zero information. Because your result is equally probable as the opposite one. You see, that's the role. Then they realize, oh, we need not only more qubits, we need to have a fidelity of each qubit to be not 98.5, but like 99.5%. Question how to do that. And that's where the problem, the issue appears that you may have heard already. It's called the error correction. So, because where the fidelity, why fidelity is going down? Because errors. You have to either fix the errors, or there are two ways. There is error correction and error avoidance. So you either want to avoid the error or just correct it if it happens. Either way, the only way to do that is to have more qubits. Why? Because if you have one qubit, what does mean error? You think it's in this position, but it's really in that position. It's flipped, for example, right? Spin flip. Okay, if you have 10 qubits as a one single coherent union, they all point in one direction. And then because of noise, one of them flipped, but 9 of them is still showing in the same direction. This tells you, so you preserve the information about the orientation. One flip doesn't change. So it costs you 9 extra qubits, but now it's much more resilient to any disturbance. And you can say, okay, 10 physical qubits gives you one very, very, very noise-resistant logical qubit. Well, roughly speaking, 1 to 10 ratio. And majority of all these error correction codes, they are the same. They always have that parameter, how many extra qubits you need to run it. Roughly speaking, factor of 10, sometimes more than that. But think about this, if it's factor of 10, to make it useful, it has to be like 10,000 to 100,000 qubits. Multiplying by 10, it becomes 100,000 to 1,000,000 qubits, right? This is 128. You can scale. Just imagine what it would be to scale at a factor of 100, for example. From 128 or 10 to what it is, 1,080 or 100, whatever. And don't forget that scaling here goes as a cube. It's a volume. It's not, the chip itself, it's easy to scale. The chip itself was like this, one will be like this, it's area, right? Area scales like a square. Volume scales as a cube plus the power dissipation. So if this is, this is the problem of the physical implementation of quantum computers. So I would say if you increase it by a factor of 10, you already probably need a dedicated building for this quantum computer with dedicated small liquid helium plant and small electrical station nearby. Well, maybe not dedicated, but at least a new transformer you will need with more powerful line. And the problem is, why? Because you have to get to each qubit. You have to set initial state of the qubit, and you have to read out the final state of the qubit after everything is done. That's basically what it is. That's problems with quantum computing. Well, what you could do in principle, like it's a type of class of problems you can do with that. Quantum simulation, it's for the, oh, by the way, speaking of this, one of the best systems, the high fidelity. How you can get high fidelity? Well, cold atoms can give you very high fidelity. is a special direction in this, so lots of, even the special companies exist already. So with cold atoms, or cold ions actually, cold ions. Well, you have, well, here they are. So you can make special connection, entangle them all, or separately, whatever. You can make them pairwise entangled and make quantum gates out of them. The problem is, it's high fidelity while they are sitting in storage and isolated. Then you have to act on them, right? Controlled not, controlled not, controlled not. So you have to take them out of the storage, move them in the action area, do the action, and then move it back again and again and again. And it physically takes a long time. So in principle, the sequence of gates could have been introduced many years ago, like out of like 10 qubits for 10 gates out of the 20 ions. The problem is the speed of assembly of the process, just physically move, interact back, is slowing down so much that you're losing the speed up of the process advantage on the way. So then many other things, so communication, cryptography, quantum information theory. Let me just go. How soon? Well, this is the D wave, the one that I told you, quasi-quantum. So it's quantum annealing. This one, that's what noisy intermediate state. This is 50 qubits. This is ions, cold ions. This is superconducting qubits, like as I told you, IBM, Google, and some others. So, but that's what you need, as I told you. So this is not my data, it's from the literature. So as you can see, as I said, million, that's what they need. They put 8 to 20 years. I'm afraid it's too optimistic. So it probably will take longer than that. Quantum communication. Another application that may benefit from quantum optics, I can make our life better. So quantum key distribution, clock synchronization, random number generation, and quantum networking. Well, a random number generation is an old problem of any network. For good quality encoding, you need to have source of randomness. So quantum mechanics gives you good randomness, spontaneous processes do that. Clock synchronization, well, also any network of regular telecommunication needs clock synchronization. And in principle, GPS needs clock synchronization. Every GPS satellite, carries the atomic clock, and with time, the clock is kind of drifting a little bit. So you would need to synchronize them. Quantum mechanics can help. Quantum networking, well, this is the most modern part that if you have a quantum computer with 200 qubits here, and another quantum computer with 200 qubits in different ways, and another, maybe that would be the way to make one big quantum computer in analogy with regular networks, computer networks. The difference, the problem, the connection between them has to be quantum as well. Quantum, remember it has to be isolated quantum system, so the connection between it has to be quantum as well. You need to have entangled states of light to connect solid state or superconducting computers. So that's another interesting area, quantum network. And quantum key distribution, that's the oldest one and the one that was operational. So what it is, quantum cryptography. Quantum cryptography, it's Alice wants to talk to Bob and encode the message so that if takes the information, she doesn't get any information, also Alice and Bob will know that someone is listening in there and stop communicating. That's the essence of quantum cryptography. How? Well, actually, the first question is why do we need? Sometimes you kind of even get surprised, why do we need secure communication? because most of our communications are impossible to understand in the first place. Maybe that's the best way to communicate. Anyway, how to secure communication? We all know that there are tons of security protocols these days, and they're different. What is a common thing about all the protocols in the world, mathematical protocols? They're all reversible. Basically, there is always mathematical program that can undo, decide. Question is how far. The more complex protocol is, the longer it will take computer to calculate. Is there any way to communicate between two parties so that no one ever be able to decipher? And the answer is here. And the answer is so old. It's a Vernam cipher, one-time pad. They call it a Che Guevara cipher because he used that. And not only him, still people use it. If you have a shortwave radio, turn it on and try to move in short waves, and sooner or later you can hear the station, and someone will be just talking numbers. That's a one-time pad communication. Okay, so what's the principle? It's absolutely unbreakable principle. You need to have a random set of particular numbers, random. And the number of these random units should be exactly equal to your message, to the length of your message. If you basically, and we'll talk more about this, how it's done, but basically if this condition is satisfied, series of randomly chosen numbers, not shorter than the length of the message, and very important, it's used only once. So it has been used in ages, since 1980 up to date. So if you use it only once, if randomness of original sequence is good, no one would ever break it. The only way to break it, if you repeat the usage of it. So unfortunately, like during the Second World War, there were some, in Belgium, was the resistance, Nazi resistance ring called the Red Capella. And they ran out of, because usually when you send your spy, you give them a book with random numbers, and you keep the second copy. And then when you used it, so you have to throw away the code, you cannot reuse it. And they ran out of codes. So they reused that, and Germans captured that, and they were able to decipher that and find them, and basically they got killed at the end. So that, but if you use it only once, then it's absolutely safe. And by the way, that's really the essence of modern quantum cryptography. It's not about coding anything. It's about the refilling random numbers between two parties. So if we start to communicate and run out of random numbers, there are two options. I make the two copies. Originally they were on paper, on books. Then there were magnetic tapes. Then there were floppy drives. Then there were CDs, then DVDs, Blu-ray DVDs, and every time you see the amount of bits per unit was growing, but still to keep active communication you need a lot of them. So you have to have a trusted carrier, basically the guy with the gun, to carry it to the other place, to give it to people there, and then to communicate, but then you exhaust it again after some time. You have to refill it. So you have to refill, meaning you have to re-establish the sequence of random numbers between one party and the other party, so with the guarantee no one on the way was listening. That's the whole essence of quantum cryptography, nothing else. And basically, well, this is quickly how it works. You take your text, you convert it to the like numbers, You used your key, add to the numbers, you transmit it, you subtract the key from this, and you get it back. And this key has to be the same, has to be random, and you have to use it only once. And between this is the key distribution element, what quantum cryptography is about. It's all based on the no-cloning theorem, that if you have a quantum state, it's quantum state of anything, including quantum state of light, you cannot make exactly the same copy. Why? Because if you start to send random numbers from Alice to Bob, encoded in the quantum system, if someone would like to make a copy, you have to measure it first. And that means you destroy the quantum system. You have to measure it, but then you cannot just measure it and that's it. Because if you just measure it, it means you kill it. You have to measure it and make a copy and send it back. So then the other party will use it, but you keep the copy so you can decipher it. So, but quantum mechanics prevents that, and that's why quantum cryptography is secure. And that's what the essence of the process. Basically, with photons, what you do, you have two polarization bases, horizontal, vertical. Basically horizontal, vertical, 0, 1, and 45 minus 45. And how it works, it's, you see, like in vertical, if you project it on the 45, it's, it will be equally superposition of zeros and ones, right? Because 45 on this, it will be one projected here, one there, and they are equal. It's called the mutually unbiased bases. So if you have in one base, but then come with the measurement device, and because Bob is measuring using polarizers, as you can see. So if it's vertical and vertical, then it will be well defined. Vertical and horizontal, nothing, no results. You put it vertical and 45, then it's either yes or no with 50-50 chance. So that's the whole principle of operation. And basically, what how it goes, you encode 0 and 1 in one of these, either in this basis or in this basis in the photons. And Bob here detects it either in this base or in that base. If, whenever if comes into the line here, if will have exactly the same apparatus as the Bob. The only thing is that you have polarizer and detector. That's all what you have. So basically, when if does this detection right here, and then make a copy and send it to Bob, then basically if 50% of time makes an error, instead of vertical, for example, detecting 45 degrees and so on, and then send it to Bob, but Bob does the same thing. So 50% here, 50% here, it becomes 25. 0.5 times 0.5 is 0.25. So 25% of error is available here if someone does the detect and resend measurement in the middle. In principle, that's really your margin of identifying the presence of the eavesdropper. If your communication with Bob gives you 100% correlation, or 99, 95%, 90%, it means clear, right? If it drops below 75, it means someone is listening. So that's basically like roughly principle of quantum cryptography.
But
Yeah.
they should have a maximum agreement of 50%. How we can say
25%. So error, if you basically, well, when I'm saying 100% correlation, so there is 50% of error, but this 50% is dropped through the communication between Alice and Bob, what base Alice has been using.
Okay.
The 50% is overhead of the communication. So they do the communication, if no even there, they do communication, they communicate bases but not states, and then 50% drops. The rest, they use small portion of it, randomly subselective, to check what the level of errors. If level of errors is less than 25%, it means it could be some noise in the system, whatever. But between 75 to 100, that's area where you can treat it as the quantumness has been preserved. If it drops below 75, it means someone with classical apparatus was measuring and resending.
You mean after distillation? That's the
After, no, it's not distillation. Well, it's basically, well, call it distillation if you want. There's lots of stages of that. We'll talk tomorrow about that in detail, in really great detail what it is.
Does it mean that we can make quantum repeater?
No. Well, actually, the quantum repeater, that's another thing. You cannot do quantum repeater because what the quantum repeater is about. Well, I mean, sorry, you can do repeater, but what's the meaning? You cannot do amplifier. The whole idea is you start with like 1 million quantum states, you start sending them, and they are disappearing due to losses. Right? That's why all quantum cryptography cannot go too far. We'll talk about this. So the idea is, okay, can we extend the distance? Now, in order to extend the distance, you need to have not a repeater, you need amplifier. Because if you have like 10 photons arriving to the repeater, you can repeat it to 10 only. And then further down, you only send 10. What's the purpose? They will disappear very quickly through the loss in the next system.
In the literature, I saw some.
Yes. Just remember, repeater is not an amplifier. The classical system solves that with amplifier. You go 80, 100 kilometers, your signal is depleting, you put an amplifier, back, another. Quantum mechanics does not allow you to amplify because you cannot make copies. Because amplification is making multiple copies of the thing. Well, it works. This is the first quantum communication network in commercial fibers in the city. This is Boston University, this is Harvard, this is BBN Technology. It was initiated by these guys because they are famous. BBN Technology, it's a company that developed all the protocols for the ARPANET, that is the predecessor of Internet. So at that time you can go and just shake hands of the guy because there were proposed protocols, and one of the protocols was email protocol. And he was the guy who decided to make all the names like this at, and then the name of the network. So he decided that would be this format, because that's what the networking protocols are about. And they decided, okay, if we did classical networking, why don't we do quantum network protocol? And that's what the result of. For 5 years, we worked together. So after 2.5 years, it started to be operational. It's been running for like 2.5 years. Until 2006, very successfully, 3 nodes, and then many other networks happen in the world around. By the way, with all the efforts in quantum cryptography these days, you can, in 2005, I put together the collection. It's not that I wrote the book, I was editor of the book. There are 10 chapters there, each chapter by very good team of quantum cryptography of particularly different types. And you can read what has been done 20 years ago already, given all the noise today about the quantum cryptography, and compare basically what has been known and what's new these days. Okay, so the problem in quantum states, you create it, you propagate, you lose them on the propagation, because loss is loss, doesn't matter quantum, classical, it's losing. So you cannot pack more than a particular number of quantum states at the source. So you can immediately anticipate how many of them will reach 50 kilometers, 100 kilometers. These days you may have seen some papers saying, oh, there's a new world record on quantum cryptography. We go 500 kilometers. Well, when I see this, I just go directly to the end of the paper and see what is the final bit rate. Secure bit rate. Okay, the latest record I've seen, it was 0.01 bit per second. You have to wait 100 seconds for 1 bit of information. 100 seconds and 1.5 minutes, by the way, for one bit of information. So for the paper and publication, that's great, but for practicality, you better shorten your distance and go to reasonable rates, and then it will work. Like 50 kilometers, for example, you can have 100 kilohertz, for example, and basically within a day, you can accumulate enough random numbers to have secure communications. Although the conventional classical technology is not staying idle either. You know, I had a friend who always was telling the story like about the transmission of quantum information, and so he said, okay, can you beat my experiment? And my experiment is throw the hard drive. If I have a hard drive with 10 terabyte, it's cost $200 today. 10 terabyte of random keys. I make 2 copies. It's a classical process of doing this. Now you can do it on a regular computer. If randomicity is not enough, run it, randomization protocols, classical things, and you have it, right? 2 copies. I give one to you, keep one, 10 terabyte. If every day we will have a video conference, like how many gigabyte do we need to do the video conference? Like 1 gigabyte per hour, right? Normal video conference, Zoom. Okay, let's say 5 hours of Zoom per day, fully protected with one-time pad. No one in the world can ever decipher what we said there, right? Absolutely. Quantum computers are useless against it. They only for RSA protocols. They cannot beat one-time pad. 5 gigabyte per day. Take 10 terabyte, divide by 5 gigabyte. How many days? Divide by 365. You don't need to refill the key. Anyway, so, but if you still want to refill the key, and over longer distances, you have an option to go to the satellite to cover longer distances on the ground. So this is the metropolitan network, this is the going to satellite. This is results from our Chinese friends in collaboration also with Austrian. They did all this 2,500 kilometers, 7,000 kilometers. You can do that. Well, this is regular final keys obtained per day. That's what it is. So that's great result, great achievement, technology and so on, but in terms of practicality, well, you can judge how many, you can send a telegram encoded with this message. It will be very hard to do video encoded with these messages, but okay. Well, it's on the good day. Like if the weather outside like today, that's absolutely fine. We can do it very nice. When it's like this, you might have a little bit of trouble to establish the communication link, right? So the yeah, basically that's it's nice, it's interesting, it's exciting, it's really a source of new technologies, but in terms of practicality, it's a good question how practical it is. The last thing is sensing and metrology. What does it mean, sensing? Quantum sensing. Quantum sensing is a very interesting area. It's kind of naturally comes from the process of learning about quantum systems. Because remember, the quantum system is isolated, right? Even to observe the quantum system, you have to spend so much time and efforts as experimentalists to carve out this piece of environment from all the natural classical pollutants for your quantum system, right? It's very difficult to carve it out, to isolate it, and observe that the behavior now obeys rules of quantum mechanics. And of course, the minute it starts to interact with something, it got disturbed, right? It's now not perfect anymore, not perfectly quantum. And how you know? Because you keep observing your quantum effect and it starts disappearing. So basically, your system becomes a natural sensor of something that interacts with this system. Like when we were doing quantum cryptography in communication fibers, we can see, feel in our system everything. The truck was passing by, the train, whatever, temperature changes, it's always visible because communication line where our entanglement was going, it was experiencing fluctuations. It's a distributed fiber sensor. If you have the cold atoms in the trap, and the energy of these atoms are used as your communicator of information to you when you observe this quantum system. If by any chance external magnetic field comes about, we all know magnetic fields interact with atomic levels, right? They start shifting. And you see that energy or the frequency of your signal is changing. And for example, if you have a detector, then like your signal is start moving away from your detector, and you can see that. That's detection of the external disturbances. It becomes a natural sensor. And today there are tons of this. Again, each one of this system is a natural sensor. That's the beauty of this. So each and every one of this is a sensor. Because you try to make this quantum, and it's always sensitive to some disturbances. So just pick up any and think which one is it, and then you will have. This is just two examples. This is the cold atoms in there, and this is the basically the diamond based. It's like I told you that NV center in the diamond is like artificial atom in the solid state, and it's much easier to operate than this guy, because this atom has to be held in the trap, magneto-optical trap over there, in the high vacuum. Here you don't need high vacuum, and so on and so on. So, but it's still an atom right there. It still is sensitive to magnetic fields. You bring magnetic field, the energy level will go around, and you can use it. And because the system is quantum, it's more sensitive than the classical ones. Again, why? Because it's more fragile. That's what it is. That's an issue of quantum sensing. Every single quantum system you ever build in the world will be sensitive to something. So just look around, identify one, and you will become an expert in quantum sensing. All right, with this I'd like to finish. Thank you.
Questions, please.
Yeah.
How are the quantum costs of gates calculated? Quantum costs.
Quantum what?
Quantum costs. For instance, the cost of the CNAT is one quantum cost.
For instance, the Hadamard cost is 5. So how can we calculate?
In what units?
In what unit? So this is my question.
Well, I don't know. You have to define the units first.
So for instance, I perform a quantum attack for a block cipher, for instance, with sleep. Then either I need to increase the number of qubits, or I need to use more than CNATs or Hadamards. So they have some cost. And
well, I mean, the question always is what kind of protection you're trying to establish. Basically, if you're saying the attack is supposed to kind of change your, it's not different from the noise protection. The idea is the same. You have to have your system that is resilient to the attack. So either you have to make, well, the first simplest one is called the redundancy. As I mentioned that. Instead of 1 bit, you take 10 of them. So, and then if 1 or 2 out of 10 get flipped, but the total is still pointing in the same direction. So that's direct evaluation of how much more do we need. The same as with gates, I think, can be scaled and but then there's others, you know, there's different basically error protection using particular type of codes, the toric codes and other things, but they are even more complex. Basically, it's a special structure that's encoded the relationship between qubits, and the idea is that they are more resilient because of the topology of the state. But the topology is the distributed feature. Topology does not belong to one item, to two items. To have topology, you have to have some structure, and that topology will be particular shape in that structure, right? So to execute this, you need resources to execute this structure and then make relationships, the shape between that. So that would be another way of protecting from error. And how much? Well, you can probably estimate what was in the beginning and what was at the end, and then rate it in terms of qubits or whatever. At the end, it will be power and size.
I have a public question.
Uh-huh.
On one hand, we have this quantum computer as an hardware.
Yeah.
On the other hand, we have artificial intelligence as a software.
Yeah.
Shall we scare about the future or be optimistic?
Well, you've seen what quantum computer can do. Artificial intelligence, as you may know, has limited capabilities. We cannot invent new things. Artificial intelligence is basically a quick search over a large database with small gradients. Like if you have, for example, 1 million photographs, and you know that somewhere in those photographs there is particular relationship between elements, the human will never be able to do that, but machine can. That's what it is. Remember, artificial intelligence always does what you train it to do. You cannot do new things. In fact, I was having the same question basically 5 years ago. I decided to learn what it is. I never studied artificial intelligence before. And I spent the whole year with first reading and then talking. And then, yeah, now it's absolutely transparent concept. Basically, you can learn how to sift through the large amount of data and get out some particular information. That's it. End of the story. We'll never create anything.
So nowhere.
Yeah. Well, unless you give the power of decision based on the criteria. So basically, the question is who is, it will give you information, and then you decide whether you will act on this information or you will give a machine the algorithm how to act on this information. Basically, if the machine will have the do nothing or just flip the switch and the bomb goes off, then the machine can do bad things. But if you don't allow a machine to do that, but only give you information, and you decide what to do with this information, then that's what it is. But other than that, there is lots of, too many promises are going in artificial intelligence, the same as in quantum computing. Yes, there are good sides and lots of positive things, but there is also lots of hype going around. So we have to be, as a scientist, we have to be objective and sort out things.
Okay, last questions, please. Only one question. One. Yes. Girl first. Yeah, ask.
Is it possible to keep the information, keep the results with regular technologies like transistors or both?
Just could you repeat this? Is it possible to get technology,
it's
the information is?
Biggest problem is we can't keep the information, results. We can't repeat it like a loop. I'm asking if we keep the results and information with our regular technologies, or like
Well, then you are the quantum domain, that's it. The minute you keep information for yourself, for observer, you out of the quantum domain. You cannot go back.
You can't
No.
keep that up.
No, because the amplitude and phase, as your information is encoded in amplitude and phase. Anytime you do the measurement to store this in your conventional domain, you erase the phase. Mathematically, you take the value, multiply by complex conjugate. You have a square of the amplitude, but your phase is gone. Because e to the I5 and e to the minus I5 is 0. So the information about phase is getting lost. What only been there is amplitude times amplitude conjugate, which is square.
So it's not possible from physics.
Now, if you want to do things, you have to do inside the quantum domain. The only way out is do everything there and do the final readout and get it out. There's no way back. Unfortunately, that's the trick of quantum mechanics. And in fact, it's the source of many handmade paradoxes in the field. Because people say, oh, here's the detector, oh, I detected the photon came from here, so I can trace it back where it came from. In reality, you cannot, because it can come from different places with different phases, but you don't have information about the phases. That's what, you cannot trace it back.
So thank you. Today time is over. Let's please tomorrow postpone all questions from tomorrow. Tomorrow we will.